Okay. Right. So thank you all for coming and thank you for the invitation. I really wanted to be there in person, but fate had other plans for me, so I couldn't come, unfortunately. I'd like to begin by acknowledging my co-authors in this, Sarah Arpin, Mingji Chen, Kristen Lauter, Kate Stang, and Ha Tran. So there was a group of 6 of us who did this. And let me start by explaining some of the terms in this title. And in particular, let me start with orienteering. So what's orienteering? Orienteering is a sport by which you're supposed to find your way across varied terrain to various checkpoints using only a map and a compass. So that's orienteering, and that's what we're going to be doing. So our terrain is going to be what's called the oriented supersingular L-isogeny volcano. Our wayfinding tool is not going to be a map and compass, but it's going to be one endomorphism. And our task is to find a path to a known checkpoint. Okay. So the territory we're working in is elliptic curves. So we have an elliptic curve over a finite field FQ of characteristic P. You should think of this as large. And then it's well known that the points on an elliptic curve over any extension field form this finite abelian group. We've seen these pictures probably many, many times. And an isogeny is simply a non-trivial group homomorphism. So it's a rational map that preserves the identity and thus becomes a group homomorphism. And it's attached to it has a degree. The degree of an isogeny is simply the degree of the map of the isogeny as an algebraic map. So it's represented by polynomials, and it's essentially the degree of these polynomials. And when the characteristic doesn't divide the degree, the isogeny is called separable, and then the degree is just the number of elements in the kernel. And the other thing we need to know is that every subgroup of the group of points on the elliptic curve occurs as the kernel of some isogeny. And this isogeny can be computed. So an explicit equation can be computed, and an explicit equation of the target curve can be computed. And this can be done by Velou's formula. This is pretty standard stuff. And I should also mention that isogenies are always surjective. Okay, that's an isogeny. So what's the isogeny pathfinding problem that we want to talk about? Well, you pick a set of primes. You should think of these primes as small, 2, 3, that kind of thing. Maybe even just one prime, like 2, and 2 elliptic curves over FQ, and you're supposed to find an L isogeny path. So what is that? That's a path of isogeny starting at the first curve and then going to another one, going to another one, going to another one, until you end up on the last curve. And the degrees of these isogenies are supposed to come from this set of prescribed primes. That's the isogeny pathfinding problem. And so the question is, how hard is this problem computationally, and how do we solve it? And another question that I didn't write down here, what does this have to do with class groups? So before we talk more about the problem, let me talk about why we want to be interested. This problem has many, many applications. One application is cryptography. There's a hash function that uses it. There's cryptographic key alignment that uses it. There's a so-called CM method that is used to construct cryptographically secure elliptic curve that uses it. So there are many applications in cryptography. You can use it to compute the endomorphism ring of an elliptic curve. You can use it for point counting. You can use it for computing modular polynomials who actually parameterize adjacent elliptic curves with an isogeny between them. You can even use it to generate irreducible polynomials. So there are many, many applications in cryptography and in number theory. So this is really a quite intensely studied problem. What do we know about it? Well, we know a bunch of things. When the elliptic curves are what's called ordinary, that just means that their p torsion is z modulo pz, or isomorphic to z modulo pz, then there's a classical exponential algorithm, essentially q to the 1/4, and a quantum algorithm that is sub-exponential. So some of you might recognize this complexity. This is the same complexity as computing class groups of quadratic fields and things like that. When the elliptic curves are supersingular, so that means they have trivial p torsion, and they're defined over fp. So the models, the equations actually have coefficients in fp. Then you have very similar complexity results, except that q is replaced by a p. And in the general case, supersingular elliptic curves always have a model that's defined over fp squared. And in that case, the complexity gets much worse. The best classical algorithm is now p to the 1/2, and the best quantum algorithm is actually also exponential. So we didn't know until recently how to do this problem in sub-exponential time, and that's what this work is about. And I should mention that concurrently with our work, Ben Wesolowski was also working on this problem and came also up with sub-exponential algorithms, but it's kind of comparing apples and oranges. So his algorithms are quite different. They make different assumptions. So it's hard to say which one's better, which one's worse. The answer is sort of, it depends, but it's good to have two different algorithms. Okay. So very importantly, a very important connection between pathfinding is to the endomorphism ring. So what's an endomorphism? An endomorphism is just a group homomorphism from an elliptic curve to itself. And then it's not hard to see that the endomorphisms form a ring. The addition is just the addition of the endomorphisms, and the multiplication is composition of endomorphisms. And this is called the endomorphism ring of the curve. We denote this by end E. And we know from the theory of complex multiplication that over a finite field, there's two possibilities for the endomorphism ring. It's either isomorphic to an imaginary quadratic order, when that's the ordinary case, or it's isomorphic to a maximal order in the quaternion algebra ramified at P at infinity. If you don't know what that is, don't worry about it. The important thing is, in the ordinary case, it's a commutative two-dimensional object. In the supersingular case, it's a non-commutative four-dimensional object. And when the endomorphism ring is O, either a quadratic order or a maximal order in a quaternion algebra, we just say that the elliptic curve has complex multiplication by O. That's the lingo that's being used. So what does this have to do with pathfinding? Well, in the supersingular case, which is the case we're interested in, it's well known that, pardon me, pathfinding is equivalent to computing the endomorphism ring of the curve. So those two problems are equivalent. What that means informally is that if you can solve one of them, you can solve the other one without too much extra work. So endomorphism rings are really important in this game. And we know that this is easy, pathfinding is easy under two possibilities. A, if the endomorphism ring is known, or if just one small endomorphism is known. If a small meaning small degree. So if you have a small degree endomorphism on the curve, then that problem becomes really easy. But the difficulty is that this is a giant if, because finding the endomorphism ring is hard. And sorry for the spelling error here. Small endomorphisms are very rare and they're extremely hard to find. So you can't really get your hands on any of these things. So what we were asking is, well, what if you try and find middle ground? And let's say you have one endomorphism available, but it doesn't have to necessarily be small. It could be a large degree endomorphism. How does that help you with pathfinding? That's the question we want to answer. So can paths be found with one possibly large endomorphism? And the answer is yes in sub-exponential time. So we need one more object related to elliptic curves. That's the J invariant. If the elliptic curve is given by an equation like this here, a short Weierstrass model, so let's just assume that the characteristic is greater or equal 5 for simplicity, then this is the J invariant, and the denominator here is 0 because that's the discriminant of the elliptic curve, and that has to be non-zero. So this simple formula gives you the J invariant. And what's important about the J invariant? Firstly, every J invariant in FQ is the J invariant of some elliptic curve, and it's very easy to write down an elliptic curve with that J invariant. Secondly, in the supersingular case, the J invariants are actually defined over Fp squared. So FQ could be a much larger field, but if you have a supersingular elliptic curve, then the J invariants are always defined over Fp squared. And the most important thing, and the reason it's called an invariant, is that it's invariant under isomorphism. An isomorphism is just a bijective isogeny. So it's a group isomorphism, and J invariants are isomorphic under this. So if you have an isomorphism from one elliptic curve to the other, to another, the J invariant stays the same. And so that way you can characterize elliptic curves by, or isomorphism classes of elliptic curves by their J invariants. That's what we're going to do. So that's the J invariant. And so what we're actually going to do is, instead of finding paths between elliptic curves, we're going to find paths between J invariants. Okay. I am somehow missing. Okay, so now let E be an ordinary elliptic curve. So let's just look at the ordinary case first, because pathfinding is a lot easier there. So let E be an ordinary elliptic curve, and then you have an isomorphism from that elliptic curve to the endomorphism ring, which is an imaginary quadratic order. And what is the connection to class groups? This is, after all, a class group conference. Well, you take an invertible ideal in this quadratic order, you make sure that the norm is not a multiple of the characteristic, and then you build this subgroup of the group of points. So you take, you map this ideal via this isomorphism into the endomorphism ring, and then you get an ideal of endomorphisms, and now you take all the endomorphisms in that ideal, and you take the intersection of their kernels. So this is the set of points where all these endomorphisms in this ideal evaluate to 0. And that's a subgroup of the group of elliptic curves, and as such, it occurs as the kernel of an isogeny. And we denote this isogeny by phi A, and the target curve is just isomorphic to E modulo EA. And with this notion, we get an action of the class group of this endomorphism ring on a certain set of elliptic curves. And the set of elliptic curves in this case is, or rather J invariants, is all the J invariants of elliptic curves that have complex multiplication by that same quadratic order. So you bundle together all the elliptic curves that have endomorphism ring O, where O is this fixed order, and then the class group acts on this. And the action looks like this. You let an ideal act on a J invariant, and you just assign to it the J invariant of this ideal here. And this action is faithful and transitive. So faithful means that only the trivial class acts, only the principal class acts trivially. And transitive means that any two J invariants are related by some ideal. So in particular, this means that this set here has class number, has cardinality, the class number of the order. And this action, this group action, is really, really important to pathfinding. It makes it computationally, it gives it a big boost. Okay. So with that, we can define the so-called L isogeny graph of elliptic curves. So we're now going to take the vertices of this graph it's just the elements in FQ, and you interpret them as J invariants of elliptic curves, okay, or isomorphism classes, J invariants of elliptic curves. So this is independent of L. L is a small prime, so you can do this for L equals 2, L equals 3, L equals 5. It has to be distinct from the characteristic. But the vertex set of these graphs is the same regardless of what your L is. So the 2 isogeny graph, 3 isogeny graph, and so on, they all have the same vertex set. But the directed edges are L isogenies. Isogenies of degree L. This is the graph that we want to look at. And so you can see that finding paths, at least paths with the, like where the degrees are all L, is the same as walking around in this graph. So we have now taken the elliptic curve isogeny pathfinding problem and somehow moved it to a graph pathfinding problem. And so we want to study this graph. So first of all, this is per se a directed graph because isogeny go in one direction, but we can identify every isogeny with its dual, and that gives two edges in opposite directions, and that makes it an undirected graph. So remember, what is the dual of an isogeny? The dual of an isogeny is just an isogeny in the opposite direction, such that the composition is multiplication by n on either elliptic curve. And multiplication by n is just if you take n times a point, you add it to itself p times. So for every isogeny, there exists such a dual isogeny. If the isogeny is an isomorphism, of course, then this is the identity. This is multiplication by 1. But in general, you may not get the identity, but you get this. This is sort of the closest thing you can get to an inverse. And so for every vertex in the graph, you have an edge going in one direction and an edge going in the other direction, and then you just identify the two, and now you have an undirected graph. Okay, all right, so that's the L isogeny graph. And now what does this thing look like? Well, it's a very, very disconnected graph, and it's almost L plus 1 regular, which means that almost all the vertices are incident with L plus 1 edges. And now why is that? That's actually very easy to see. Because every isogeny, remember the degree is the number of elements in the kernel. So every isogeny has a kernel that has L elements. So that's a group of order L. And in particular, that group is annihilated by multiplication by L. That group sits inside the L torsion. And the L torsion looks like this, Z mod LZ by Z mod LZ. So here now, every edge, every isogeny corresponds to an order L group in this E of L. And there's L plus 1 such groups. So there's L plus 1 edges. Okay, so this is true for almost every vertex, except for 2 of them and their neighbors. Those are the J invariants J equals 0 and J equals 1728. And they're very nasty and very ill-behaved. So they like most literature on elliptic curves just exclude those two because they cause a zillion problems. And the reason is that the invariant j equals 0 has complex multiplication by the Gaussians, and the j invariant 1728 has complex multiplications by the Eisenstein integers, and you recognize those two quadratic orders as having extra units. And this means the elliptic curves have extra automorphisms. And of course, you can compose these isogenies with automorphisms and get different isogenies, but it's still a degree L isogeny. So there's some extra weird edges in the graph at that point. So that's why the L+1 regularity doesn't hold across, but almost everywhere else it hits. That's the ordinary. So the ordinary curves, and the ordinary curves are distributed over a lot of different connected components, but the supersingular curves all sit in one component. There's about p over 12 supersingular curves, so not that many, but they all lie in one connected component, and that's what's called a Ramanujan graph. At least when p is 1 more 12, because then you don't have those two problematic j invariants in there. So this is an optimal expander graph. So what is such a graph? Well, it's a graph where if you start walking along your L isogenies, then you don't have to go very far until your walk is sort of indistinguishable from actually a random walk. So it has good mixing properties. Like you start walking and then you end up very quickly at very random points informally. And this is actually really good for cryptography. This is why these things are popular for cryptography. So that's the supersingular components. And now the ordinary components are what's called volcanoes. So now we finally got into our volcanoes. And the ordinary components look completely different from the supersingular ones. So here's a picture. On the left is an ordinary component. This is for L equals 3. I don't know what the field is here. And you see it's a very beautiful, regular looking, kind of organized object, right? Here's L equals 3, which means every vertex is incident with 3 plus 1, so 4 edges. On the right is a supersingular component. This is actually for L equals 2, so every vertex has 3 edges incident with it. Left side, nice and orderly, very organized. Right side, totally chaotic. So you see that the game for supersingular curves is very, very different from the game from ordinary curves. But so on the right is the object we want to navigate, not on the left. This mess on the right is where we want to do our pathfinding. So in order to do that, we have to understand how to do it on the left and then somehow try and impose the kind of organized structure on the left onto this messy piece on the right. This is what this talk is about. So let's first talk about these volcanoes. So let's do some volcanology. So what do I mean by a volcano? A volcano, first of all, this is a graph that has a unique cycle. And that's the rim of the volcano. The cycle could be degenerate. It could be just one vertex or maybe one edge. So it may not be a real cycle, but oftentimes it's a real cycle. So let me go back for a second. You see that there's this one. Let me see if I can do something like this here. Here is this one nice cycle. It's the only cycle, right? And every rim vertex is the root of a full tree of the same height. A full tree means all the leaves are at the same level, and they all have the same height. So let me go again to the back here. You see here, every root here, like every vertex, for example, this one here is the root of this tree here. And all these trees have the same length and all the vertices are at the bottom. So that's what the volcano is. Okay. And the height of this tree is this object here, VL of Fp. VL is the L-adic valuation of this thing, F pi. And what is F pi? F pi is the conductor of the Frobenius order. So the Frobenius is given by mapping 2 points, mapping a point, the coordinates just to the q's power, and that satisfies a quadratic equation. And as such, it generates a quadratic order, this order, and this is the conductor of that order. That's the height of the tree, okay? And then the nodes at level k have complex multiplication by an order where the conductor is exactly divisible by L to the k. So again, let me go back to this picture for a second. So here, these are all orders where the conductor is not divisible by 3. The next level here, the second level, is all orders where the conductor is divisible exactly by 3. And the outside here is all orders where the conductor is divisible exactly by 9. Okay? So very, very orderly. And the class group action comes into action here via the rim. So if you take your little prime L and you take an ideal above it, a prime ideal above it in the rim order, the top order there, then the ideal class L acts on the rim. lets you walk around the rim vertices. And in particular, the size of the rim is the order of that ideal class in the ideal class group. And we're going to see that you walk the rim via this class group action. So the class group action significantly facilitates rim navigation. Okay, so walking in this graph has many, many applications again. So for example, if you want to walk down to a floor, to walk down the floor, what can you do? You can, for example, determine if a curve is supersingular or ordinary. It's not the best way to do this, but the reason is you just walk the full height, and if you still haven't gotten to the bottom, you know that the curve is supersingular. You can compute endomorphism rings by locating exactly, for every prime in the conductor, you locate exactly the level in this volcano, and that tells you exactly how many copies of L divide the conductor, and you do this for every prime that divides the Frobenius conductor, and that's how you get the endomorphism ring. You can do point counting, I mentioned that before. Walking the rim, for example, is used for computing Hilbert class polynomials, and they also have applications in cryptography, finding cryptographically secure curves. Also modular polynomials. So modular polynomials actually characterize the edges. The modular polynomial is a polynomial in two variables, and if you stick in two J invariants, you get 0 if and only if there's an edge between them. So again, walking in this isogeny graph has a lot of applications. And now let's look at the supersingular case. So this is an expander graph, I already said. It's a messy object, very, very messy object. And the problem is the following here. See, all the ordinary elliptic curves had complex multiplication by an order in one quadratic field. And it's exactly the quadratic field corresponding to Frobenius, which is actually this quadratic field. So all the orders, all the endomorphism rings sit inside this quadratic field. For the supersingular curves, this is no longer true because the endomorphism ring is this four-dimensional object. And so if you want to identify a quadratic field, well, there's of course many, many, many quadratic fields that sit in this four-dimensional object. And so we can no longer use this nice quadratic endomorphism structure to navigate ordinary curves. So this is the reason why pathfinding is so much harder in the supersingular case, because you don't have this organized structure. Okay, now how do we fix this? Well, that's where the orientations come in. So orientations to the rescue. So we will now answer the question, our work answers the question, if you have one endomorphism, and you can think of orientations and endomorphism as sort of more or less the same thing, how do you do pathfinding in the supersingular component? This is what we're working on. Okay, so what is an orientation? Well, you start with an elliptic curve, doesn't have to be supersingular yet, could be either, and then you pick a quadratic field. And the only restriction is that the characteristics should not split in this quadratic field. So there's lots and lots and lots of quadratic fields that satisfy that. And then it is well known that this quadratic field embeds into the quaternion algebra ramified at P at infinity. And that's the endomorphism algebra that contains all the endomorphism rings of the supersingular elliptic curves. And K sits in there up to isomorphism. And what's an orientation? An orientation is simply a map that maps this quadratic field into the endomorphism algebra. So you take the endomorphism ring, you tensor it with Q, so you allow sort of rational coefficients here, and that's the endomorphism algebra. And we know that this is a maximal order in the quaternion algebra ramified at P and infinity. That's the endomorphism ring, and every endomorphism ring sits inside this quaternion algebra, and this is just an embedding of this quadratic field into this quaternion algebra. There are many, many, many such embeddings, okay? But this is one of them. That's a K orientation. So for example, we already saw that for ordinary curves, you can always pick your field like this, and then these embeddings are actually isomorphisms. Okay, now we want to actually not work with fields, but with quadratic order. So we take a quadratic order of this field, and then what you have is an O orientation. For an O orientation, you simply require that this order O is actually mapped into the actual endomorphism ring, not just the algebra, but the ring. And then in order to get as close as possible to the complex multiplication case in the ordinary case, what you do is you require for a primitive O orientation that the image is actually equal to the endomorphism ring intersect the image of K. And for ordinary curves, you can always get this. So primitive embeddings are exactly the embeddings that correspond to the O, where the O is the actual endomorphism ring. So this is a generalization of these quadratic endomorphism ring structures that you get in the ordinary case but this will now work in the supersingular case, except your choice of K is a free-for-all, right? You have tons and tons of fields K to choose from here. Whereas in the ordinary case, there's only one sensible field to choose, and that's this where's my mouse here? That's this, oops, sorry, that's this Frobenius field here. Okay, and so now what can we do with this? So let's take an elliptic curve and an orientation. And so now we want to see what we can do with isogeny. Oh, so yeah, so we want to see what we can do with isogenies. So what we want to do is the following. So you have an isogeny with an orientation. You have an elliptic curve with an orientation. You have an isogeny, and that goes to another elliptic curve. Now that elliptic curve might have a completely different orientation by a different field. But that's no good because you don't get any structure with this. I mean, if this elliptic curve has an orientation by this field and another one has an orientation by another field, that doesn't do us any good. So we want to somehow make sure that we're using the same field for all the elliptic curves when we move along isogenies. And so for that, we compute the induced orientation. The induced orientation is simply obtained with this formula. So an orientation maps into the endomorphism ring. So if I stick in a field element, I get an endomorphism. So I of alpha here is an endomorphism, and I prime of alpha is also an endomorphism. And then you compose it with the dual of your isogeny on this side and the isogeny on that side, and you divide by their degree, and I get another endomorphism. And that's the induced orientation. And another way of expressing this is that we want this diagram to commute. So you have here, you have the two curves with an isogeny. Here you have the curves with an isogeny. Here you have an endomorphism. Every element in alpha induces an endomorphism. And then you want to make sure that the induced orientation is this endomorphism is defined in such a way that this diagram commutes. You can go along either arrows. Okay. And that attaches orientations to isogenies. And so now we can take pairs and let isogenies act on it. How do you do this? Well, first you take the image of the curve, and here you take the induced isogeny. And now with that, we can define an isogeny graph. So you fix an imaginary quadratic field. So just like in the ordinary case, we're only going to work with one field, and all the elliptic curves are going to have orientations by this one field. And so the vertices are now pairs consisting of J invariants and orientations. So the J is a J invariant, always sits in FP squared in the supersingular case, and the iota is a K orientation. And then the edges are these things where you map oriented vertices to each other in such a way that the isogeny respects the orientation, or the orientation respects the isogeny, whatever you want to think of it. Okay. And the structure of this graph, well, wait for it, drum roll, they're volcanoes. But they're infinite volcanoes. They don't have a floor. They still have a rim, and they still have the nice lava flow structure, but they're infinite. They go on infinitely often. They have infinitely many levels. And the reason is that every J invariant occurs infinitely often. In fact, it occurs infinitely often in every volcano, in every connected component. But it has a different orientation attached to it every time, because there are many, many ways to embed this quadratic field into the endomorphism ring. The thing is still L+1 regular, except near our two problem J invariants. And the vertices at level K are now precisely those J invariants where you have a primitive orientation. So we have a very similar structure. So this is really nice. Now, orientations are sort of a horrible thing to understand. And I remember it took me a long time to wrap my head around it. So we don't really want to work with orientations. We want to work with endomorphisms. Endomorphisms are something very concrete. They're maps. You specify them on generators, and then you know exactly how to evaluate them. And so let's abandon our orientations and let's just work with endomorphisms instead. And let's understand once and for all what the connection is. Well, if you start with an endomorphism, then it satisfies a quadratic equation. And let omega and omega bar be the two roots of this quadratic equation. These are complex numbers. They're complex conjugate. And that gives you two orientation. One maps omega to theta, and one maps omega to its dual of theta, or equivalently the conjugate of omega to theta. So every endomorphism gives you two orientations. Well, that's no good. I mean, we would have wanted to have some one-to-one correspondence, and instead we have sort of a one-to-two correspondence. But fear not. So the problem is these vertices may be different, but they kind of look the same. if you look at the two vertices locally in the graph, so you sit on those two vertices and you don't look too far, the environment looks exactly the same. What that means is, well, it's the same J invariant, they sit at the same level of a volcano, they have the same neighbors, when you start walking isogenies, you get the same path. So for all intents and purposes, they look the same. So what we do from now on is we take an endomorphism and then we just work with one of the orientations. And we don't care which one. For navigation, it makes very little difference. So from now on, forget about orientations and let's go back to endomorphisms and think of every elliptic curve in our graph as attached to an endomorphism. So that's the endomorphism, the one endomorphism that we're going to work with. Okay. All right, next. So let's take an L isogeny and let theta represent the orientation on E. And let's assume, so what we want to do is we want to use this graph now, we want to find a wayfinding tool via this orientation. We're going to assume that this theta satisfies a certain normal form. I don't want to get too much into this, this is technical, but you can always get this normal form by translating by a suitable multiplication by Nmap. This is not so hard. Let's just assume this has the right form. And then you have the following. Remember, what's the induced endomorphism? For the induced orientation, you take your endomorphism, stick your isogeny in front of it, stick the dual behind it, and divide by the degree. The degree is L. So this is the endomorphism attached to the induced orientation. And now, now let's think about the following problem. I sit in the graph, I see L plus 1, I sit on a vertex, I see L plus 1 oriented edges going away from me. I don't have a clue which ones go up in the volcano, which ones go down in the volcano, or if I'm even at the top. And this is what I want to figure out now. And the way you figure this out is the following. You look at your theta in normal form, and let's assume that L does not divide it. And then you can identify the direction of your isogeny as follows. If this theta prime that you compute here is divisible by L squared, then your edge goes up towards the rim. If it's divisible by L, but not by L squared, then you're at the rim, you're at the top, and you're walking around the rim. And if it doesn't divide theta prime, this thing, then your edge goes down. So this divisibility by L gives you a way of detecting the direction of your edge and actually also walking along your edge. There's another method using the eigenvalues of this endomorphism acting on the L torsion, but like people have also used this, but the problem is you're working over the L-adics, and every time you traverse an edge, you lose precision, and it's a bit complicated. So I just want to mention this is not the only way to do this, but this is the way that we used. And so now, here is how you do pathfinding. First connection to the class group action. We now have a very, very analogous class group action. So once again, you take an elliptic curve oriented. This is the primitive order. And then you take, again, an invertible ideal. And you form the same ideal. This is just like before, except this iota here is now our embedding. And then you get a class group action. And there are subtle differences to the class group action. It behaves a tiny little bit different. So firstly, it's not only faithful, it's actually free. This is a stronger condition. It's fixed point free. That's what free means. It has no fixed points, but it's no longer transitive because it may have two orbits. It may have one orbit or two orbits. And the orbits are related by the Frobenius endomorphism, the one that maps everything to the qth power. That Frobenius either leaves both orbits fixed or it swaps them. Okay, and the set that's being acted on is exactly the oriented J invariants that have primitive, where the orientation is primitive by the same order. Okay, and so once again, we can use this action to walk the rim. So this is again the connection to class groups. And so now we want to use this oriented isogeny graph to find a path from a curve E to another curve where we assume two things. One is we assume we have an endomorphism on E, given by this orientation. And two, we assume that the target curve has a known endomorphism ring. So the target curve could, for example, arise from the J invariant 0 or 1728, where we actually know the endomorphism ring. Okay, so here's what we do. You first need to pick a good field by which you want to orient. So what does this mean? You mean you have to calculate the discriminant of theta, and then that defines an order, and then you need to somehow find a field such that, right? I mean, the discriminant is conductor squared times the discriminant of this field. Okay, So you need to find such a field. And of course, for computational purposes, ideally find a field that's pretty small, that has a small discriminant. Now you have your orientation, and that defines your L-isogeny, your oriented L-isogeny volcano. And now what you do is you take your first curve and you start walking up. And we now know how to walk up. We now know whether an edge goes up and how to walk it up. So you start walking up. So you try an edge. If it's the wrong one, try the next one. Try all L+1 edges at every vertex. There's not that many. L is small. One of them goes up. You walk that one. So you walk up until you hit the rim. Okay. Now you take the curve with known endomorphism and you orient it by the same field. And this is possible because we know the endomorphism ring. And now you play the same game. You walk up from that curve as well. And now you cross your fingers and you hope that those two curves, the endpoints of these paths where you go up, that they lie on the same rim. There's actually no reason for that to happen, but you just hope and cross your fingers. And if not, well, you're going to start over again with a different field. Okay, but if they lie on the same rim, now you got your path, right? You walked up from the one elliptic curve, you walked up from the other elliptic curve, you connect them along the rim, there's your path. And now you forget that there were ever any orientations, and now you have your path. And that's how you do this. And what I want to do is I want to walk you through an example to see, so you see how this works and you see the class group in action. All right, so this is a fairly small example, but you see even that is pretty involved. So we start with a prime 179 and we work over the field F179 squared. This is generated by a square root of -1 and we work with two isogenies. Okay, so you have a 3 regular graph. Every vertex has 3 edges. And we want to find a 2 isogeny path from this curve to this curve, where the subscripts of the curves are always going to be the J invariants. So this curve has J invariant 120. It's defined over FP squared. And this curve has a known endomorphism ring, and it has J invariant 1728. So this is our task. And here's a picture. This is the oriented volcano. This is the messy, random, unoriented graph. This is the path we want to find. I don't know how well you can see these numbers. Here's your 120. And so here's your 1728. And so we want to walk from this 120 here to this. And the path, well, we walk first this blue piece, then we hit a rim. So we just walk a piece of the rim and then we hit a red piece. In the oriented volcano, this looks very beautiful. Here's your 120. You walk up this blue piece. You walk up this red piece. Happily, they're on the same rim, so you somehow connect them up on the rim. And you see here, these vertices all have numbers, 17, 28, 22, 61, and so on. That's the J invariants, but some of them are written as like J1 and J2 and J3. Those are J invariants defined over FP squared. I didn't want to write them into this picture because it's already messy. So that's these J invariants. Okay, so what we're going to do is we're going to work on the left side here, and then that finds us the path on the right side. Okay, so let's get started. So first we need to orient our field. And so we need to get our hands on an endomorphism on E. And that's already really hard. And we put Sage math to work. And sure enough, we found an endomorphism and it's got degree 288. So it's defined by polynomials of like degree 288. So it's this massively huge thing. Okay, but that's the game. I mean, small endomorphisms are rare. So you got to find big ones. This is actually pretty lucky. This is a pretty small one. So it turns out that you can actually do a little bit better. Remember, we needed the endomorphism in the sort of normal form. It turns out if you translate by multiplication by -10, you get another endomorphism that has slightly smaller degree, 188, and it's got the right form. So now we're good to go. And this has the desired form, and you compute the discriminant, and the discriminant is 4 squared times -47. And so we're going to orient by the field Q adjoint square root -47. So we were pretty lucky and found a small discriminant. So now we found a field by which we orient. And so we also see that this discriminant is divisible by 2, in fact, by 2 squared. So up we go. So we know we're not at the rim. And this picture showed this, the blue path. So we now calculate the blue path. So here's what you do with the blue path. So the isogenies, you work them out via Veloux formula. So this is so we now have our E120, we have our theta 120. This is the first isogeny, so it's degree 2 here. The target curve is this curve. This is all Veloux formula. Then you calculate the new endomorphism with this typical formula here. This is how they were defined. This thing is still divisible by 2 squared. So we know we still have to go up one more. So this is divisible by 2 squared. So the whole thing's divisible by 2. Next isogeny is this, next elliptic curve is this, next endomorphism is this, and lo and behold, so this thing is divisible by 2, but not by 2 squared. When you divide it by 2, you have no more 2's in there, so this is at the rim. So now we're at the rim. So this is the blue path that we walked up. And this is all done with standard tools, composing endomorphisms and Veloux formulas and so on. Now we need to walk up from the other elliptic curve. And remember, this is an elliptic curve that had to have known endomorphism ring. This curve has known endomorphism ring. A basis is given by this, I 1 plus pi over 2, and I times 1 plus pi over 2, where I is this endomorphism. It maps x to iy. I is the square root of -1, and pi is Frobenius. And algebraically, I squared is -1, and so I squared is multiplication by -1, pi squared is multiplication by our prime -179. This is true for any prime. This is what the endomorphism ring of this curve always looks like. So that's our known endomorphism ring. And now we need to orient this curve by that same field. And we're actually kind of lucky because one of the basis endomorphisms is already oriented by this. So we can map this, we can orient with just this endomorphism. And the endomorphism, if you express it as a rational map, it looks like this. That's degree 47. That's one way to do this. But in general, as you see, these endomorphisms tend to have really big degrees. So what you want to do instead is you want to actually express them as a product of small endomorphisms or small isogenies. And this is actually what we want to do here. For these small numbers, this doesn't make much sense. But for bigger numbers, this technique is much better. So an alternative approach is to find another endomorphism. So we won't work with the first one that I showed you. We'll work with a different one. And we find one that's a product of 2, 3 power smooth isogenies. So it's a product of isogenies, of powers of isogenies where they all have degree 2 or 3. And this is the factorization we want. We find one, this one and this one. The first one goes from E171 to E1728. It's a degree 3. And the second one is degree 16. So this is actually a much better representation. And we find that this is still divisible by 2. So we know up we go. We're not yet at the rim. Okay, so we go one up. So we compute this red path. Okay, so we now have to divide by 2. So this is the new target curve. And I didn't write down the isogeny. And this is the new endomorphism. This has degree 3. So it's a product of these two isogenies. One goes from this curve to this curve, has degree 3. The other one goes from this curve. I've already written this in factorization, so you divide by 4 here. This has degree 4, and this is a product of two new guys. This is the dual of this phi. This is the psi that we have from the previous slide. This is a new isogeny that has degree 2. So you compute these factorizations. I don't want to get into the details how you do this, but you can do this. And then you look at this endomorphism, and it turns out it's not divisible by 2. So you're now at the rim. So you've walked your first path up, you've walked your second path up, and now you're at the rim. And now you got to connect them up. So now you got to start walking the rim. And we're going to walk the rim from this elliptic curve, from this node here, E22 theta 22. And here is now where you see the power of the class group action, because this is actually much more efficient. So let's start walking, and I'm going to walk you through one step of this. So here's the step that you need to do. This is the first edge that you traverse in the rim. And remember from the class group action what you need to do. You have this prime idea L above 2 in this case. That's the rim, that's from the rim order. And you need to compute this subgroup here. Okay, and you need to compute this isogeny. So here's how you use the class group action to compute this thing. The rim order turns out to be the maximal order. That doesn't have to be the case, but in this case, it happens to be the maximal order. It just has to be an order where the conductor is not divisible by 2. It doesn't have to be the maximal order, but it happens to be in this case. So this is a generator of the maximal order, and now you need to translate that generator to the world of endomorphisms. So you need to take the endomorphism corresponding to this, the orientation corresponding to this endomorphism, and pull this omega back into the endomorphism ring, and you compute rho. This is not so hard to do. So let's say we have this rho, we can compute this rho. And now you need to compute this prime ideal above 2. This happens to be this ideal generated by 2 and omega. And now you need to calculate this ideal, this subgroup here. So remember, this was the intersection of all the kernels. But of course, all you need is the kernels on the generator. So you really only need to intersect the kernel of the generator 2 with the kernel of the generator rho. So you only need to compute 2 things. Now, the kernel of the multiplication by 2 map, that's just a 2 torsion on the curve. So you only need to compute the 2 torsion and this kernel. So you only need to compute the kernel of this row restricted to the 2 torsion. So it's real easy. Now, 2 torsion is totally trivial to compute because the 2 torsion of an elliptic curve is always just the points that have y-coordinate 0. So the identity and these 2 points. So you stick it into Sage, it computes it real quickly. There's 4 points. Now you let this row loose on them and 2 survive. So row on 2 of these points, this guy and this guy is 0. And so this is the subgroup that you have. And now you use Velou's formulas to calculate the isogeny that has this kernel and calculate its target. And this isogeny turns out to be this isogeny. This is the target curve. I didn't write down the isogeny, but Velou gives it to you. So here you see the power of this class group action. Walking rims is real easy from this class group action. Okay, so this is why the connection to class groups is so important. So this is the first edge. You now traverse one edge in this rim. And then you now still have to calculate the induced endomorphism. You do this the usual way. Okay, so that's one step in the rim. So now we calculate the entire rim like this. So this was this green rim here. Okay, the rim happens to have length 5. You also, I mean, each of these guys is attached to an endomorphism, but I didn't bother writing them down. And 5, why 5? Well, it turns out that this field actually has class number 5, and this prime ideal above 2 generates the class group. Remember, the order is the length of the cycle, so this happens to be the class number. And happily, remember I said like the 2 paths that you walk up, the endpoints don't have to be on the same rim. Well, happily in this case they are. And we actually, for the fun of it, calculated the entire rim, but if you just want to calculate your path, here it is. And now you forget all the orientations, and you forget that you were ever in this nice oriented object, and there's your path in the supersingular isogeny graph. So this is how you do this. Okay, I want to mention a couple of other results. So actually, I want to mention our algorithmic results now that you've seen the algorithms in action. So here's, there's a lot of in algorithmic ingredients. I don't want to get into standard elliptic curve stuff, I'm just going to skip this. Suffice it to say that all our code is at this GitHub repository. So we haven't worked out the example and annotated it yet, but the code's all there if you want to see it. I want to conclude with our 2 big complexity theoretic algorithmic results. The first is about a classical algorithm, and the second one's about a quantum algorithm. So I'll state these theorems fairly informally, but the papers have very formal statements. But here, it's complicated enough, so I'll state them informally. Start with an elliptic curve and an endomorphism, and the endomorphism has degree D. This D, unfortunately, generally is pretty big, and it has discriminant delta. Now, suppose that D is sufficiently large. I mean, if for small degree isogenies, this is all easy. If endomorphisms, this is all easy. So we're only interested in the large one. This can be formalized sufficiently large. And let's assume that theta can be evaluated efficiently on points of the elliptic curve. If this is much of the time, let's just assume this. You can state the complexity result in terms of the time it takes to evaluate points. But again, let's, for simplicity, assume that this is efficient. Now let delta prime be the so-called L fundamental factor of delta. So what is this? You take your delta, you pull out as many L squareds as you can, and what's left is delta prime. Well, you have to be a little bit careful for L equals 2. You might leave, because basically this delta prime has to be a discriminant. So it has to be 1 or 0 mod 4. But anyway, you pull out a bunch of L's, and that's delta prime. And let's assume that that's not too big. That's a reasonable assumption. In most cases, it isn't. Then there's a heuristic classical algorithm that finds an L isogeny path from E to a curve of known endomorphism ring, and it has this length, log P plus H delta prime. What's H delta prime? It's the class number associated to the order of delta prime. It's essentially root delta prime. And the runtime is this. The runtime, and you see here, the key thing is the runtime is sub-exponential in the degree of the isogeny. It's polynomial in the size of the prime, but it is linear in this class number. But this class number generally is not so big. If you find a relatively small field by which to orient, then this class number is not big, right? I mean, this was like 47 in our case. So this is not so big. The key here is that the runtime is sub-exponential in the degree. And if you have your isogeny given in this factored form that I showed, where it's like just a product of isogenies of small degrees, the runtime improves significantly, and the sub-exponential dependence on log D actually goes away. And it is replaced by a polynomial dependence on the bounds of degrees of the isogeny. So in our case, this would have been 3 or 2 or something. So this works pretty well. Our second result is for a quantum algorithm. So here again, you have an endomorphism of degree D and discriminant delta. You're assuming that the degree is significantly lesser than delta, and this is normally the case. And again, this is a reasonable assumption. You assume point evaluation is efficient. Then there exists a heuristic quantum algorithm that finds a smooth isogeny from the elliptic curve to a target curve of known endomorphism ring. This is the norm of the isogeny. And of course, if you have an isogeny, once you factor it, you have a path. The smoothness bound is sub-exponential, this time in the discriminant, not the degree, so slightly bigger. And the runtime is also sub-exponential in the discriminant. So this is the sub-exponential algorithm. There's some constants here. We didn't bother working those out. And this algorithm, if you know something about quantum algorithm, it uses what's called vectorization, and it solves this problem here. And this is a really hard problem. Given a supersingular elliptic curve oriented by some order, find the corresponding primitive orientation. And Wesolowski in his parallel work did not consider this problem, but this is a hard problem. You need to solve that in order to solve this problem. So those are our two big results. So the conclusion is one endomorphism is enough for pathfinding, as long as you're content with a sub-exponential algorithm. Classically, the runtime is sub-exponential in the degree and linear in a certain class number. It can be significantly improved if depending on how your endomorphism is given. Quantumly, the runtime is sub-exponential in the discriminant. And the last thing I want to mention is, of course, well, we have paths to a curve of known endomorphism ring, but of course, that gives you arbitrary paths, right? You have two elliptic curves, E and E prime. You find a path from E to a curve of known endomorphism ring. You find a path from E prime to a curve of known endomorphism ring, and then you just put the paths together, and then you have a path. So this is no restriction. These are the two papers. They're on arXiv, so you can find them, including all the references. And with that, I'll finish and take questions or answers.
Thank you, Renate. So any questions?
I have a question. Hi, can you hear me?
Yes, I can hear you.
Okay, so I'll probably speak up. What if, so in the middle you are talking about two different volcanoes, right? So what if you go around the rim and don't find the other elliptic curves?
Yeah. Yes, I see. What happens then? Good question. I should have said this. In the is this the classical algorithm? No, this is the quantum algorithm. So you have to work out the probability that those two things are on the same volcano. Because that gives you the expected number of times you have to try. And that's exactly this class number thing. That's where this class number dependent comes from. So the expected number of times you have to try this is exactly the class number. Does that answer your question?
Yeah, so I was just wondering, do you have any special choices for K? Can you choose your K suitably so that you're more likely to have the two elliptic curves the same one? Do something?
Choosing K is really hard. I mean, you're lucky if you can sort of find a good one at all. You know, if you start imposing additional restrictions on it, it gets really hard. I mean, in the example, I can tell you, we tried lots and lots of small examples until we found the one that I presented with that nice small discriminant of -47. Like much of the time, you know, I mean, because it means you have to find an endomorphism on the curve, and that's really, really hard, right? So you're sort of lucky when you find one, right? So some sort of recipe of how you find a good one, no, you just got to try and hope to be lucky, right? Because that's the hard part, finding an endomorphism on a curve. That's exactly the problem of finding a small endomorphism on a curve. And that's a really hard problem, right? So you basically have to be lucky.
Okay, thank you.
So anyone else? Yes, Mike.
Can you hear me, Renata? There's a big.
If you speak up, I can hear you.
Okay, maybe.
Yeah. Just know the problem of finding those Ks, that are they known to exist?
Sorry to interrupt you. I can actually hear you worse now.
Oh.
You were really quiet all of a sudden.
Just a minute.
Yeah, just a sec.
Switch.
How about now?
Good enough.
Okay. So, yeah, the question, just to follow up, so do you know that suitable fields K exist for which you can find a reusable automorphism?
Yes, but you may have to, I mean, you may have to work with a different endomorphism, right? I mean, I sort of glossed over this, but we started with this endomorphism of size 288. And then we translated it, and then you got one of 188. So now, of course, the discriminant changes. And then later on, we found yet a different one, and then the discriminant changed again. So you may have to fiddle around. You like the first one you have, you may not be able to work with, but you have to find one where it works, right?
Okay.
So they always exist, but finding them is a different story.
Yeah. Okay, and the second question is, so what is it about adding the orientations that helps you get the sub-exponential complexity? Is it just that you can get to the rim of the volcanoes quick?
Yes, it's really that you have the same structure as in the ordinary case, and so you can sort of get close to the right, because you now have a navigation tool. You now in the super singular graph, there is no up, down, rim, nothing, right? Here, there's a well-defined up, there's a well-defined down. Well, we never go down, right? And so you know where to go. And so that gives you a chance of finding a short path rather than walking around randomly and never getting anywhere, right? That's really it in a nutshell. It's the structure that gives you that, right? The orientations give you that volcano structure, and that gives you a navigation strategy, right?
Got it. Thank you.
Anyone else?
Okay, so anyone from the online audience? Okay, so let's thank Renate once again.
Thanks very much.
So we after 10 minutes. So